I'm Panchami, and this is Mahima. We are from Cyber Labs, Indian Institute of Information Technology, Kotte. Here we are presenting about a cryptographic research project. It's all about a secure, privacy-preserving, lightweight authentication scheme for healthcare systems based on Internet of Medical Things. So as our application is related to the healthcare application, we just start from the Internet of Medical Things, which it's a network, IOMT, it's a network of interconnected medical devices, hardware infrastructure is there, software application which connect the healthcare information technology. The basic application of this IOMT is that we can remotely monitor the health condition of the patient. If you want to have a medical emergency, like if you want to connect with doctors, or medical emergency like ambulance services, then we can make utilize of this network, and effective tracking is there, and it completely supports this healthcare system management. For example, we have all gone through the pandemic phase, right? So when the pandemic hits the worldwide, like thousands and millions of people lost their life, and they were affected, or plethora of people were affected and went into quarantine. So with this patient being quarantined, the health condition ought to be monitored. And as this much number of people, we cannot accommodate the whole number, this much number in a hospital. So they have to be monitored remotely, so that these contagious diseases we cannot, like, the complete quarantine should be there. At the same time, these vitals of the patient have to be remotely monitored. So there comes this technology, like the IOMT came to place, where it plays an important role when it comes to the healthcare management systems. This is just an architecture view of this IOMT, where you can see this sensor node. And when it comes to sensor node, obviously there will be sensors which could really sense the vitals of patient. And from there will be a processor, it could be a microcontroller. Then there comes the communication module is there. We can use Wi-Fi or Bluetooth or LoRa. Then the vitals which is sensed from these devices will be sending to a gateway. It could be either sense the servers or even our mobile phone, which could act as the gateway. So from the gateway, it's connected to a cloud, or even nowadays the blockchain is being connected. Then the server is there, IoT servers, where we can do permanent storage or this analytics, and the decisions could be taken place over there. Based on that, the actuations may happen. So while we consider while we consider the application, the medical application, it's more regarding, it's a crucial, it's like a do or die condition. So the latency, we cannot tolerate the latency. At the same time, of course, the communication is there, security plays an important role, and efficiency, the performance should be considered with the minimal cost. Why it is minimal cost? Because we are dealing with IoT device, which is a lightweight platform, we call it as the resource constrained devices, which is constrained in terms of memory, processing, or the power. So in that phase, we have to consider the security needs, as this is all about the communication. The data coming from these devices need security. Of course, privacy should be there, and we have to come up with the we have to secure the data. So how it could be done, right? So then comes the CIA triangle, the confidentiality. If you want to come up with the confidentiality, the best way is the encryption. And of course, there are plethora of other schemes are there, but like if we come with the encryption, yeah, so there is a burden of key. The symmetry key, literature says that the symmetry key is the best thing to ensure the confidentiality. And when it comes to confidentiality here, the key management is a burden, or we have to handle the key management, how it will be done. At the same time, we have, this is a very dynamic network, this IoT devices, where we have the users, the patients, then in between this emergency services, there either it could be a doctor or a ambulance driver. So it's a very completely dynamic network. We are putting together and coming with a secure communication. In that phase, we have to authenticate the users. So our agenda or our basic objective of this research is to have a secure authentication and a key management scheme to have a very efficient, good performance playing and with minimal cost of this IOMT communications. So there comes the possibility of AKA systems where authentication and the key management is being considered in our research. So we have taken around 12 research papers, and the reference we have listed all over that. So while considering way from 2019 to 2020, 23 papers, so yeah, so while considering the existing schemes, there are few gaps we have identified where most of the schemes are intensively depends upon this central authority. Say central authority means if I'm a patient, if I'm communicating, I need some emergency service. Okay, so in between it could be an ambulance driver or some doctors. Then in between there will be a server. We call it as a central authority. So I want to communicate with the central authority. From the central authority, it will communicates to the third person. The replay is in the same way itself. So the latency is so high, and the dependency towards the central authority is very, very high in the existing systems. As well as this network is completely dynamic, this anonymity is not preserved when it comes to the users. So that's the second gap that we have identified. The third one is, of course, the platform, this IOMT platform, which is a resource constrained platform, which we have to consider the limitations, where we have limitation in the storage, processing, of course, the power limitations are there. So if you apply a security protocol over this platform, so we have to be well prepared in terms of this lightweightness or the resource constrained nature. So we come to the point that while we apply or while we come up with a security solution, there should be a good trade-off between the performance, security, and the cost. So there we come up with the problem statement, like to design a secure, privacy-preserving, lightweight authentication scheme while achieving good performance with minimal cost and to reduce the dependency on the central authority. So this is our research problem. Next, about our objectives, the major contribution of this research work is to analyze the existing lightweight authentication algorithms. So we have already defined what are the gaps that we have found it out, and coming with the design of a secure privacy lightweight authentication with minimal dependency on this central authority. After that, once we have designed, we have to analyze how much performance it is, or is it secure. And so the next step is that the performance is analyzed in terms of communication and the computation cost. Lastly, we have already analyzed the security. We have done the security analysis through two ways, informal and the formal. And the formal will which is handled using the band logic, which is a mathematical proof, and which will be, the whole thing will be narrated by Mahima. And so the formal analysis we have done through the mathematical proof of band logic, and we have implemented and verified this security algorithm in a security verification tool called Scyther. Apart from Scyther, you can use Avispa or Pro Verifier. Then lastly, we come up with the informal analysis, where we prove that it's resistant against major attacks like middleman attack, or the anonymity is preserved, or the backward and the forward security. So most of the attacks we have come up with the proof through this informal analysis, and that's the objective of this presentation. Yeah, coming to the proposed system, we will just start with the network model. So here you can see the patient. We are assuming this patient is having the wearable sensor, and the mobile device is associated with the patient, and mobile the sensor node, which there will be sensor, the microcontroller, and this Wi-Fi module. We call this is a sensor node, and it is of course bounded with the body of the patient, and it's connected to the middle node, which is the mobile. So we claim this is the patient device. Okay. As part of this future scope and all, you can either classify into phase 1, phase 2 itself in the sensor and the mid node. So we have come up with the concept of the patient node is assumed that the patient is having this sensor node and is connected to the mobile device. Next comes the ambulance driver, or it could be a doctor where exactly this patient needs help in terms of emergency situations. There comes the hospital, where we call it as the trusted authority, hospital trusted authority. So these are the actors in our proposed scheme. And while considering the flow, first of all, if I am a patient and I need help, so first I have to register with this central authority. Of course, there is a need of central authority over there for the proper registration. And once we get the ID and the authenticator, we can have a peer-to-peer communication with either to the doctors or this emergency services. Okay, so that's a basic agenda. So first we have to register to the hospital authority. So we get the credentials. Then once we get the credential, like we call it as the authenticator, we can directly have a peer-to-peer communication with the ambulance driver with preserving anonymity. So that's our project is. And coming up with the proposed authentication protocol, basically there are three phases: the initialization, the registration, and the authentication phase. These are the few notations that we have used. So initialization phase means, initialization will happen either between the patient and the hospital authority. We claim the hospital authority as the central authority, or between the ambulance driver and the hospital authority. The basic aim of the initialization is that to have a secret key between the patient and the hospital authority. Next is coming to the registration. Again, it is happening between the patient and this hospital authority to get the authenticator. Once we get the authenticator, the authentication can be done with the patient directly towards this ambulance driver or doctors or whoever it is. We can establish a very secure peer-to-peer communication while preserving anonymity using this protocol. So that's our network model. Coming to our proposed system in detail, it's more regarding cryptography. So basically we have the three phases: initialization, registration, and the authentication phase. We have completely utilized the cryptographic protocols or the algorithms to design the novel authentication scheme and the key establishment scheme. So on one hand, it's authentication; on the other hand, it's a key establishment as well. So we call in general it is the AKA schemes. Yeah, so first the initialization is happening between the patient and the hospital authority, where this phase we completely utilize the ECC based, elliptic curve based cryptography, which is the public key based infrastructure. Elliptic curve based Diffie-Hellman structure we have utilized, so that the patient have to pick a random number, and that random number seems to be very private, and from the random number we are going to generate a public element, P of PA, we call it as the public element. Along with that timestamp we are generating, we are sending towards the hospital authority. We say that's the first message. So why we are using this timestamp? Because to resist against this replay attack. Okay, so if there is an adversary between this patient and because we are using internet, right? So if there is the adversary, what the end user will use, what the receiver will use is that they will find out the time interval we compute the time interval and the value enable. Okay, so it's the upper bound of the communication. If the condition is satisfied, then we will move towards the next phase. If it is not, that request from whoever the patient is, it's rejected. Okay, so it's to ensure there is no replay attack is happening. Replay attack is not happening. So once it is being received from by the hospital authority, the same set of things will be happening in the hospital authority, where it randomly pick the number which is very private for the hospital, and from that it generates the public element, and this public element is being shared towards the patient. So the agenda is that both the parties will communicate the public elements between themselves. Okay, so once they get the public elements, they can able to create the secret element, the same secret element. For example, we call it as SV of HYPA, and on other hand SV of HYPA. So this is the same secret key which is shared between this patient and the hospital. This is very same, and we have utilized the ECC based Diffie-Hellman structure for this initialization. And here the next is about the registration. So we have shared, or in between the hospital authority and this patient, a secure key is being generated among those parties. Next, for the registration, we have to get the authenticator from the hospital authority. So of course, in a normal communication, a patient will choose their username, password, then it's already the key is there, right? So we can encrypt whatever the message passing from the patient to the hospital authority, so that it's encrypted, and this hospital authority can decrypt this with the same SK. And once it is decrypted, SK will create an ID of for the patient. Along with the ID, an authenticator is also be created, and this ID authenticator is being sent towards the patient. So the basic objective of this registration process is that to get the ID and the authenticator between this patient and the hospital authority, which is acting as the central. So this is an initial phases. Once it is there, we can have a secure communication between, or secure peer-to-peer communication between any party in the network. While considering it's a dynamic network, between any party we can have a very secure communication. Authentication will be established, of course. Key management. After the key management, we can communicate with the party, with an unknown party, in a very secure way. Okay, so when it comes to authentication, of course, as I said, most of the existing algorithms or the existing AKA schemes is not preserving anonymity. Here we are coming up with the anonymity. So what we do is that this ID of the user is being sent to a hash function. Here we are using the SHA-256 function, and so that a pseudo ID is being created. Okay, so this pseudo ID, so we are very familiar with this mobile applications like Ubers, and also that the pseudo ID of the ambulance driver or whoever the participating or the entity is, that we will get that public key elements. So I'm saying that, hey, I want to communicate with you. So this is my pseudo ID, this is my public key, and this it's yours. This is my authenticator. So that this ambulance driver, while or whoever receiving this message, they will create the key. So after creating the key, there will be an authenticator should be created between that authenticator. We call it as Y of AD or Y of PA, and using this authenticator, it's proving the authenticity of between two anonymous users, and hereby we are establishing a secure communication. So while receiving this message M2 by the patient again can coming up with there is no replay attack is being happened with the help of this timestamp. Then the key is also being, this K is the private element, the same K is being generated, and whatever the authenticator received, this same authenticator is being generated in the patient side or whoever the user is. And the received and the generated authenticators or the values are being shared or it's being compared. If it is same, we will ensure the authenticity of the user. At the same hand, or on the same, on the other hand, the session key is being shared between the two parties at the same time. Okay, so we have established a secure authentication scheme as well as a key management scheme. Once we get the key, the message being sent with the key with this any symmetric algorithm you can deploy. We are suggesting a lightweight encryption algorithm over here, and a secure communication could be ensured between the two anonymous parties. So that's a proposed scheme. Here we analyze the performance in terms of communication and computation cost. The communication cost we have analyzed in such a way that in between the parties, some messages is being sent, right? So M1, M2, M3. So if any in these messages, you can see if we consider M1, there are some parameters is being sent, right? So each parameter having some bits. For example, IDs, we have taken 64 bits, and authenticator, as it's mostly we are creating authenticators with the help of the hashes. So the resultant bit will be 256 as we are using SHA-256. So while adding all these bits, which is being shared between the parties, we can get the communication cost. So M1 plus M2 plus M3. So whatever the values we are shared, we are computing in terms of bits and then computing the communication cost. Okay. So here in this communication cost, you can, while we are comparing with this, we play an important, like we plays a significant role because we have come up with a very reduced communication cost over here. Then next is about the computation. In our proposed scheme, we have utilized the hash SHA-256 XOR and symmetric encryption. So 5 times we have used the the basic cryptographic function. 5 hashes we have used, 1 symmetric function, symmetric encryption, and 7 XORs is being used. So the time taken to execute a particular cryptographic function, and so if we are computing 5 times or 6 times, we will add all the values, then we get the computation cost. So the computation cost is calculated based on the total time taken for the execution function. In our proposed scheme, we have used SHA, hash, symmetric encryption, and XOR. So there we can come up with 0.07934, where it's also I don't claim that it's the lowest one because we have our own justifications, but we come up with the same computation and the same computation cost with the existing schemes. Okay, more or less same. Okay, so in that way, we claim it as that the performance it's good with respect to our proposed system, and the security analysis will be handled by Mahima. Thank you.
So security analysis is something like as cryptographic researchers is very important, right? So like when you have a product, you can give it to your customers or internally you can test it, right? But when you're deciding and designing protocols, like you need to have models, like how do you test if your cryptographic algorithm is best? So that's the relevance of here. And like here me being again a penetration tester turned cryptographic designer, like researcher. So it's very important to have like methodologies to test our systems. So that's what formal analysis does. We make use of existing tools, automated tools, or even like models, mathematical models, and we actually evaluate the security of the cryptographic protocols. So one such automated tool is Scyther, which is selected by us. We do have other automated tools as well, which you can definitely explore. Scyther is one of them. In Scyther, you can actually specify the security requirements. So if you are targeting at secrecy, right, you have an element that you should ensure that at the end of the protocol or even after the lifetime of the protocol, it should be kept secret. So is that being achieved? So this particular tools, by defining this security requirement, it helps us in ensuring that that is achieved. So it does have automated functionalities and algorithms, logics running behind it. And what it does is, it will simulate attacks on the model. And we will be able to ensure that that particular element, which I targeted to keep secret, is actually kept secret. An adversary will be brought into the structure. An adversary will try to like steal the element at each communications. So ma'am was showing a dialogue model, right? So at each levels, the adversary will be trying to steal the element, and that is how we will be able to ensure that that secrecy is kept. Similarly, we have other security requirements like alive, which ensures that, see, you keep certain elements important in the protocol, but they should be participating, right? If you keep somebody in the protocol structure which is not very active in that, they can turn or they can be a vulnerable point inside the protocol structure. So that's what alive ensures. Weak agree is what? Like the responder should be believing something like we are trying to establish. Like simple thing is like handshaking stuffs we use, right? So the basic principles comes from that. You should be agreeing to what you are like trying to achieve. So that's what we ensure here. Then non-injective agree is again similar to that. Commit and reachable is actually like reachable is one of the important parameters we look for as designers of like authentications or even communication protocols. So what it ensures is that you have a trace through which the claim can be reached. So you try to achieve a claim, right? Secret, let it be any claim. So that particular claim should be achieved or reachable, right? So that's what reachable ensures. So for this, we actually have languages, which is called security protocol description languages. This is one run, so I'll just show you. So this is how you define the actors. It's not very clear, but the role, the different roles is like here the patient and the authentication element. So what we are trying to do is we are having claims here. So this is the language. I just wanted to give you a brief on the structure that it is having. So these are the claims. See, what I'm trying to do is I have to ensure that this AD is alive, and this AD, this particular role is actually agreeing to whatever this person is like telling, and all of the communication stages. So this is actually the simulation structure. So this will give you an idea being from computational background. So what it does is, it will run the protocol for multiple iterations. So this is like the run 1, and this will be run 2. In the run 2, what it will take is remaining traces. So there will be some elements that was exchanged in that, which might be a nonce, right, or a communication that. So what it will do is, in the second iteration, what it will do is, it will start from there, what is remaining. So if it is dying out, it will see. Likewise, it will go for many iterations. So what it enables us is, like, it will be able, giving us possibility to simulate all the possible activities that can happen on remaining traces. Like, you can treat each of the communication dialogues as one node. So whatever is not dying out in each node, it will start from there and see if an adversary will be able to obtain a private element. It's very interesting, like you can explore. Next is actually a mathematical model. It's like little more not even programmed. like it's mathematical. So what it does is, it gives you a technique to actually formally write down and prove that whatever claims or the goals that you're trying to achieve is like achievable. So here we have certain goals. So I'll just give you a brief. So this band logic does give us few rules, like jurisdiction rule, message meaning rule, nonce verification rule, beliefs rules, etc. And we do have certain assumptions. Like when we are, like for example, I'll give you an overall picture. So in this scenario, the authentication scheme we designed, we are believing that anything that is originating from the hospital, the data that was given to the somebody from the hospital is trustworthy, right? So that is what is called assumptions. So what it is showing us, PA is believing that this originated from there. So this is the notations that we use. Like, I'm not getting into details, of course. So what it is showing us, it gives you a formal way of proving that your goals are achieved. So we do start with a formal goal. We do have certain rules. We do take assumptions, and we derive and reach the goals. If we are able to reach the goals, it means that our protocol is secure. So here the rule is that PA believes that this particular thing originated from PA, right? And ADS also believes that this is also originated from that, like what it is trying to do is, the value that is generated both the ends is same. It's simple as that, but notationally we write it this way, and we do prove it mathematically. So that is band logic. Next, we also have informal security analysis. So I hope what is formal analysis and informal is sort of clear. Formal is actually using automated tools and mathematical models. And informal security analysis, we sort of use the cryptographic tools or the structures that we have in the protocol, try to compare them, try to define them, and show that our protocol is very good. So, for example, the last row is ours, and we have taken many security requirements. I'll explain one of them. Like for example, mutual authentication, though, like it's very clear, right? What it happens is, like the patient and the, like let's say, ambulance driver, so both of them should be able to authenticate and know that it's actually talking to the patient, this particular patient with this identity, and that ambulance driver is trustworthy as well. So that is mutual authentication. So we are proving that we do achieve mutual authentication. Then another criteria, which is user anonymity, which was one of our major objectives. So you can see that SR3 is not being achieved in many of the protocols. We do have it. So how we achieved is, we never share the original identity of any of the participating parties. Like the communication parties will never share their original IDs, will share their hashed versions. So what it achieves is, we achieve user traceability. Sorry, user anonymity. So likewise, we did prove that we achieve many of the security requirements in good authentication protocols. So coming to the conclusion, we did target on achieving privacy of the users, especially since it is healthcare management system. We gave high priority on to maintaining the privacy of the users while achieving lightweight features. So that was our major target, and we did achieve it, which was very much described in the computation and the communication cost as well. And we did formally and informally prove that we were able to do this while maintaining the security parameters. So these are the few references. Yes. Thank you.